Hello and welcome back. Welcome back to the A4Q Global Testing Summit. I am delighted to now welcome Adam Roman and his exciting presentation about the TQED model. This is a very simple but effective technique for boosting the tester's creativity in designing test cases. Adam Roman is a professor of computer science at the Jagiellonian University in Krakow in Poland, and his research interests include effective test techniques, software quality metrics, as well as models and mutation testing. He authored several books and papers on software testing, and we are really looking forward to your presentation. I now hand over and have a lot of fun.
Thank you very much. Welcome, everyone. I'm very glad to be here. Today, I would like to talk about this so-called TQED model, which is really a very simple but quite effective, as we can see later, tool for increasing the tester's creativity. And the agenda for this talk is as follows. First, I will talk about motivation. So why at all to speak about such things. Then I will say a little bit about models, because it's important to understand what are the models and what is their role in software testing. Then I will go to the TQED model in particular, describe it. It will be very short thing because the model is really simple. And then I will show you some 2 or 3 practical examples how to use this model and how to, for example, detect some bugs in Google applications using this very simple technique. And last but not least, I will show you that this technique really works, and we know that because of the experimental study we did on students at our university. So first, the motivation. When you go to conferences, read some books, read blogs, this kind of stuff, you usually hear about test management, test organization, test process, all these things that are here on the left-hand side of the slide. And that draws the tester's attention most, usually. What doesn't, maybe testing itself. By testing, I mean creating good, effective tests which can detect defects with high probability. Why is it so? Why this testing itself, the most important thing in our profession, doesn't attract so much attention? Because it's difficult. The test ideas which we want to use in our software testing must be aligned with the context in which we perform our testing. They must be very concrete, and they have to depend on this context. So they differ across projects, and that's why we usually talk a lot about processes and about how to organize this testing and test management, but we don't really talk much about this particular concrete techniques that allows us to provide effective test cases. So the question is, can we at least try to do this? Can we generalize this test approach? Seems to be a hard and difficult task, but at least we should try. We should try and see what happens. And one way of thinking about this approach is through the models. We can do this through models. So what are the models? That's the first question here. Here we have on this slide, we can see some definition of a model. So a model is a representation of an idea, an object, or even a process or a system that is used to describe and explain phenomena that cannot be experienced directly. That's the very important feature of the model. So when we can't repeat 1,000 times some experiment, for example, we have this rocket which goes to Mars or whatever, we can't create 1,000 prototypes, send them and see what happens. We need to simulate it somehow. So we need to use some models of this rocket or whatever. So these models are a visual way of linking our theory about the world, with experiments. So they guide research by being simplified representations of an imagined reality that enable predictions to be developed and tested by experiment. This is the scientific approach. In fact, the science works this way. The science goes through experimenting with things, seeing what happens, and then adjusting our theories so that they describe the world better, and so that we can make predictions about this world more accurate. So this is a model. But what does it mean to us? What does it mean to testers? We can slightly modify this definition by changing some words in this way. So for us, we will say that a model will be a representation of software that is used to describe and explain bugs or defects that cannot be experienced directly, or at least at first glance, because as you know, we have to do sometimes really hard work to detect some bugs. And these models will be a visual way of linking development of the software with its execution, and they will guide testing by being simplified representations of this imagined reality that in our case will enable to detect bugs with higher probability. Now, as you know, there is this saying that all models are wrong, but some of them are useful. And now the most important question here is what makes the model useful? So what characteristics should a model have to be a good representation of this reality that we are modeling? So a model should have several features. For example, it should model the problem domain correctly. It should be simple. So, of course, the best model is the reality itself, but it's too complicated to experiment with. So, model must, by definition, be some abstraction, some simplified description of this reality. It should be easy to understand. So, it should also speak the right language. It should be flexible. So, we should be able to use this model in different contexts, and this will be also very important characteristic in our context, so that we can provide some generalized approach to all different types of testing. A model should be also generic. It should be we should be able to use it in many different situations, and also it should allow us to make some predictions. So we would like this model to give us some clues about where we could expect some bad things in our software under test. So once we have this model, the next question is how to verify its appropriateness. So how can we say that the model works well? How can we verify it in practice? We can do this by scientific method. I will show you at the end of this presentation this experiment, which will show how we verify the model's appropriateness. But first, let's go back to testing. Before we define the TQED model, let's go back to testing, and let's think about how we can describe software. Here, the inspiration comes from physics, because, as you know, in physics, we have a small number of notions, of definitions, of laws, which can be combined together and describe even the most complicated reality. Physics has only several concepts that describe the world around us. So, for example, when we want to describe this volcano, this process, we can describe it with several characteristics. And here we can define the following four, I would say, characteristics or dimensions of the reality, which can be then transferred to the software world. So first we have quantity. We have some amount of these ashes, and also in software testing, the quantity can be here in this example on the right side. We can see that, for example, there is some value of a variable or some constant, some number. These are some quantities. These are things that can be described by quantity. Then we have some events like eruption. Here, calling a function can be considered as an event. We have data. We have some concrete physical objects in the real world, like this lava. Here we have a variable, for example. It's a concrete, durable thing, durable in time. And we have this time dimension. So time is a very natural concept. So here, for example, the time can be represented as a sequential of execution of sequence of instructions. So in the same way as we can describe the world, we can describe software. Even the most complicated software can be described using only these four concepts, in fact. Data, events, quantity, time. Of course, it depends on the level of abstraction, because we could go deeper and deeper and deeper, and we can create very, very complicated descriptions, but we can do this. Of course, we will stay at some reasonable level of abstractions. So we can describe any software using these concepts. So exactly as every physical phenomenon can be described as a combination of these basic physical terms, we can do the same with software as a combination of these, let's say, basic software dimensions. So that's the inspiration from physics to provide some four simple characteristics that can describe our software under test. And now the TQED model, it's a very, very simple thing. It looks like this. So we have this four characteristics. We have data, we have events, we have time, and we have quantity. And we can also combine them. So we can model some phenomena in this software testing world as a combination of different dimensions, of different characteristics. For example, some phenomenon can be considered as a combination of two events, let's say, or three events or four events. These three dots here mean that we can go with more and more combinations. So this diagram shows only basic characteristics and also only two combinations of each dimension. So we have data plus data, we have data plus event, we have event plus event, and so on and so on. Now, what can we represent by these four characteristics? It depends on tester and on the problem, of course. But in general, data will be considered as any durable in time, any object which is durable in time. It may be input data, it may be cookie file, it may be file name, it may be configuration item, any kind of document, whatever, right? A button, a field, some element of graphical interface, user interface. These are things that we can consider data. Some, I wouldn't use the word physical because it's not physical, but in some sense, some physical elements of the software. Then we have events. Software acts in a way that there are some instructions that are executed one after another. So there's something that happens in this system, right? Something is executed, something is defined, something some value is assigned to some variable. Someone clicks a button, some message arrives to some system, someone invokes a method, someone is fulfilling some rule, someone is computing something. These things we can consider as events. So these are like things that happen. We can in general say that these are things that happen. Speaking about time, we can imagine different concepts related to time. For example, time dependencies. For example, the concept of one thing being before another one, or two things happening in parallel. Or we can use it to describe some sequencing, some repeating, some persistence, some constancy, that something is constant and doesn't change in time, and so on. And then we have the fourth dimension, the fourth characteristic, which is quantity. So we can describe here we can describe quantity as for example, as with the concepts of emptiness, like there's an empty set, so set which contains nothing. There is some uniqueness, something is in one copy only. There is some minimal value in some range. There is some maximal value. There is something just below minimal value, some average value, some typical value. This is the concept of being a part of something, being a subset of something, being a superset of something, and so on. And using these concepts, we can describe many different things that happen in software. So now let's have a look at two very simple examples and one more practical example of how can we use this approach in software testing. Suppose we have a ticket machine. It's shown here on the left. We have a ticket machine. We can put there some coins, some banknotes, some money. We can select which kind of ticket we want to buy. We can cancel the operation. We can finalize the operation by clicking this buy button. Then the ticket machine will give us in this dispenser, it will give us the ticket. It will maybe return some change if it's necessary. We all know how does this kind of machines work. So what can be a data dimension here? So this physical object, it may be ticket may be a type of data, it may be ticket card in the machine, it may be coin, it may be a banknote, it may be some value of total price of the tickets we want to buy, and so on. What can we consider as events here? Well, if someone presses a button, this is an event. When the machine gives a change, this is an event. When someone is inserting some coin or banknote to the machine, printing the ticket is the action, it's the behavior of this machine, it's an event. Switching it on and off is a kind of event. Canceling the operation is also an event. As for time, we can consider, as I said before, different concepts of time-related concepts like long, short, or typical periods of time, this parallel thing, this constant thing, and so on. And for quantity, as I said also before, we can consider low values, high values, boundary values, maximal values, and so on and so on. So the tester can define basing on the context, on the system under test, these dimensions, these things, this data, events, time, and quantity. And then the tester may try to somehow combine these concepts, and this will result in creating some test ideas. During this process, the tester may think about some things that they can verify. For example, imagine that this tester analyzes the specification of this machine and identifies three following dimensions: denomination of the money, it's a data object. We have boundary value, which is a quantity object, and we have total price, which is another data object. And now the tester may consider these first two objects, the denomination and boundary value. When we combine these two ideas, the tester may now there's the time where the creative process comes. The tester may think about how to combine, how these two things can combine together, and they may think about the concept of using the coins with minimal denomination. For example, we had this 5 cents was the minimal denomination we can use, so this is some partial idea. Use some coins with minimal denomination. Now, considering the quantity, boundary value, and data total price, combining them together, the tester can come up with an idea of buying the tickets for the maximal possible price. Yeah? If we combine total price with boundary value with some maximal value, we can think about such an idea. And then once having these two partial ideas, use coins with minimal denomination and buy for the maximal possible price, we come up with a test idea, which can result in a test case, in our case. Insert only the coins with the minimal denomination for the highest possible price, which is able to, in this specification we could only buy, I think, 10 tickets for 380, so it will be $38 max. So that's an example of a test idea. Another example, again, we can consider 4 dimensions: pressing a button, cancel, quantity a lot of, and time a long process. Pressing a button together with a lot of gives us the idea of buying a lot of tickets. You can imagine that a user clicks this button, buy ticket, buy ticket, buy ticket. Then buying a lot of tickets with cancel gives us the idea of repeating the whole process again, and then combining it with time, we come up to a very interesting idea of how to define the cancel operation in this machine, in this interface. Should it cancel only the last ticket we wanted to buy, so reduce the number of tickets by 1, or should it cancel the whole operation? And that's not a trivial question in this case, because it's an issue about the system design. We can't really answer easily to this question. So this is an example which shows that this method can give us some clues about design, about the software design, not only about testing the system that is ready for use. And another example with Google. Sorry for Polish language here, but I think all of us use this, or most of you use this Google Calendar, so it shouldn't be a problem. You know that we put there some title and the date of the event, and here we click save, and then we have this event in the calendar, in the Google Calendar. So we have clearly data, which is event name and the hour, or the date and the hour, and kind of event, which is clicking this button save or create the event. Now, when we combine several dimensions like event name, hour, a part of something, more than one, and this kind of stuff, we can come up with an idea that we can create an event in this calendar which contains number and hour, which are separated. So we use numbers, but not in the hour, but in the title of the event. And for example, if we, again, sorry for Polish language, but I will translate it. If we have a meeting which is called meeting in a room 1-to-1 at 12:30, if you do something like this in Google Calendar and press enter, it will create an event at hour 1:21. Why? Because it will treat this 1-to-1, this room number, as a time. It's very weird. I think it's still there in Google Calendar, this bug, because it's clearly a bug. And it's very interesting that the Google Calendar, whose main function is to operate on times and dates, can't really recognize a very simple string, which could be like, matched with regular expression or whatever, and provides us the wrong time here. So these are the 3 very simple examples of how it works. Now, does it really work? Does this method really help us? How can we verify it? We can do it through the controlled experiment. So we did this experiment. The experimental design is shown here on the slide. So we had 2 groups of people. One was using this TQED approach. Another one was a control group which didn't use it. All of them had to test 2 applications, provide some test ideas for 2 applications, and then there were independent testing experts who evaluated these ideas in terms of creativity factor. We used humans here. We couldn't really calculate this creativeness because it's a human factor, so we used experts to evaluate it. And the experts didn't know which test idea comes from this TQED model and which does not. So they didn't know that. They just evaluated the test ideas on some scale 1 to 4, where 1 means this idea is trivial, everyone can come up with it, and 4 was for very creative ideas, non-trivial, which have a big chance to detect some bugs in the software. And then we compared the evaluation of one group with another. So from the statistical point of view, the groups were equal. It's very important in this kind of experiments that the groups are like the same, so we can compare them. And then they had to test two systems. There was a parking gate and library. The difference was that these were two different, very different systems, because we wanted to check whether the model works, whether it's universal or not. Does it work only for some specific kind of system or for all of them? So parking gate is a physical system with a behavioral aspect, and it's user-centered. And library was a system, a software system with a very important part, which is the business logic behind it. So there were some rules and stuff like this, and it was back-end oriented. So these were quite different systems. And then after the experiment, we compared the experts' evaluations on this creativeness of the test ideas. And the result was that for this TQED group, the evaluation, the mean or the sum of these factors was higher than, was greater than the mean value for this control group in both cases. In case of this parking gate, it was the statistical significance is 0.07. It means that the result is significant statistically. Experiment B is, let's say, on the border, but still we can say that the difference is not because of some random factor, but because of using this TQED technique. Also, when we looked at the number of ideas that they come up, so for parking gate, TQED invented 28 unique ideas, which the control group didn't come up with. Control group came up with 12 such ideas, and both groups came up with 46 ideas, which are common for these both groups. In case of library, TQED group came up with 23 unique ideas, the control group with 12, and there were 50 common ideas which occurred in both groups. And the mean value of this creativity factor is shown here. So here, again, it's greater for TQED than for control group. Here, it's more or less equal, let's say. So the conclusions are that this model seems to increase the tester's creativity, which was here understood as the ability to design a test with high probability of failure detection. And so we can argue that using this method allows us to create better tests. There are, of course, some threats to validity. We did this experiment on a small group of participants. They were mostly students, not the experienced testers. But anyway, the study shows that there is something, clearly there is something behind this model, and it can be used in practice. Actually, it was used in one company. A friend of mine took this idea and went to his company. They had this so-called it's called bug bashing session or something like that. It's the event in which a group of testers together try to find as many bugs in the application as they can. And he said to me that in his company, he said it really helped them, but unfortunately all of this stuff is so top secret that they didn't allow me to say anything about this experiment, except that it worked for them. So I think it may be a useful tool for testers. Some more details are in my book, which I wrote some time ago. It's called Thinking-Driven Testing. One part of this book is about this model, and the conclusions are this. I presented you this model. I showed, I think you see that it's universal, very simple, very effective and useful. It's no rocket science. These concepts that this model uses are nothing new. They are like well-known concepts. The only new thing is that you can combine them somehow in this creative way to create some new ideas. But you have to think, you have to remember that no matter what kind of model or technique or tool you use, models cannot replace thinking. So there is always this creativity factor. So these ideas, these basic ideas that we come up because of our creativity. the model cannot do this for us. The models really cannot replace testers and this rational or creative thinking. And by using the scientific method experiments, we confirm that the model really works. So yeah, science is great. Thank you very much.